So for this week, let's talk about the idea of causation. We undertake causal research in order to determine if a factor causes another factor to happen. So does X cause Y? Because we're always trying to figure out explanations for why things happen. So think about if you got a speeding ticket today. Do you wonder, had I not been going fast, would I have gotten this? Had I taken a different route, would I have gotten the ticket? If I'd left a little bit earlier or sooner, right? We wonder about everything in the world around us. So when we apply this critical line of thinking of causation to our own lives, it becomes very nuanced and complex, and it can even feel a little bit threatening. It's really easy for us as humans to think about cause and effect when it comes to things in the natural sciences, right? Like gravity causes things to fall towards the object with the largest mass, for instance. So what goes up comes down. But we don't always like applying it to us and our behaviors as human beings. So what we're basically doing to determine causality is that we're taking one variable and we're saying we're holding it at a constant state, and that we're going to use that variable to predict a change in other variables. Now, this is a very complex form of research, and what we end up finding is that we can never be 100% sure that there are not other factors influencing the causal relationship, especially when dealing with human beings. And this is one of the biggest differences between the natural science and social science. In the natural sciences, I can work with everything in a vacuum, and I can reduce all the factors down to just the factors I'm interested in. We cannot do that with human beings. There are often ethical considerations. We can't lock someone in a bubble and do an experiment on them. And there are often deeper psychological considerations that even the respondent may not be aware of that may motivate their behavior. Now, often when we're talking about causation, we're talking about what is known as the deterministic view. And that is to say that if X causes Y, once X happens, Y will follow. And Y has no say in the matter. It has no choice. So this deterministic view is an absence of free will, and it kind of flies in the face of what we believe about human behavior, because we want to believe that humans make all their choices on their own. Now, while we may be threatened with the idea that we do not have free will in what we do, we also demonstrate this lack of free will in the way that we talk to each other about things in our lives. So think about how many times you may have said, I can never date someone who smokes or does drugs or drinks too much. Think about how you might have said, I can't tell my father, mother, or priest that. How often, though, have you ever said, I choose not to date X, Y, and Z or tell this person X, Y, and Z? When we start looking at it from this angle, do we really even think we have free will? By creating reasons for why we won't do something, we're actually creating causes and we're denying our personal choice. So let's talk about the concept of correlation. Correlation implies a relationship. It relates to the closeness of objects, people, events, things like that. So for example, people often believe that there are more bizarre behaviors exhibited when the moon is full. But is that really true? Do people get wild when there's a full moon? Or do people believe that it is okay to be wild when the moon is full, so they act in that way? This is why it's a correlation and not necessarily a causal relationship. So correlation exists to help explain the intensity of a relationship between any two variables. It indicates both the strength of the association and the direction of the association. So what I mean by the direction of the association is that if one goes up and the other also goes up, that is a positive relationship. But if one goes up and the other goes down, that is a negative relationship. It's often denoted using the Pearson's R coefficient, and it describes a linear relationship between two variables. Now, when we talk about the strength of the association, the value of Pearson's R can range from 0 to 1 or -1. The closer it gets to 1 or -1, the stronger the relationship. And that tells you whether it is a positive relationship or a negative relationship. It is often expressed as a percentage since it only goes from 0 to 1. So you could say something might have a 72% positive association between the two variables. When we are trying to establish causality, there are 4 basic things that we look for. The first and most important is time order. You have to know that X comes first in time to cause Y. You can't say smoking causes lung cancer if every single person who has lung cancer did not start smoking until after their diagnosis. We also have to have what we call covariation. This means that the changes in the independent variable has to create changes in the dependent variable. Third, there has to be some logical and compelling reason for why these two variables are related. This leads us really to the fourth one, which is non-spuriousness. Sometimes two variables appear to be related, but they're not. There's a third factor that is actually maybe causing both, or causing one, or mediating the effect, or moderating the effect between them. The most famous example of a spurious relationship is that when sales of ice cream go up, so do murders. But do murderers go get Ben and Jerry's after committing their crimes, or does eating Ben and Jerry's make you want to go kill someone? Of course not. These are spurious relationships. And there's a third factor that's not being accounted for that actually causes both, and that would be summer and heat. As it gets warmer, people are more likely to eat ice cream. Also, many murders happen during the warmer months because people are out and about with each other, and people might have higher tempers, and the heat causes that to exasperate their feelings and make them want to harm someone else. So it's not the ice cream that leads to the murder, even those things are nearly perfectly correlated. It's the heat that causes both. Now, it is never possible to actually prove causality in social science. What we can do is show the degree to which causality is probable. Now, you probably heard it said a million times that correlation does not imply causation, and I can show you again the ice cream and murder assaults known correlation that exists. But, as I said before, this is a spurious correlation, okay? So correlation does not imply causation because there are other factors that can cause the effect to be observed. This is why we start talking about in public health this idea of necessary versus sufficient causes. A necessary cause is a condition that must be present for the effect to follow, and a sufficient cause represents a condition that will pretty much guarantee the effect. So in social science, evidence of either a necessary or sufficient cause is often used as the basis for concluding a relationship as causal. So for example, being a female biologically is a necessary condition of being pregnant. Being female, though, is not a sufficient cause since you can be biologically female without being pregnant. In another example, you can be convicted of a crime because you were judged guilty. So being convicted of a crime is sufficient cause of being judged guilty. But it's not a necessary cause because you can still be judged guilty if you confess to the crime. There are also seldom absolute cases of either sufficient or necessary causes, and never cases of both. So, for instance, having sexual intercourse would be a necessary cause of being pregnant, but it's not absolute because you could get pregnant through artificial insemination. And since the great majority of pregnancies result from intercourse, it makes sense to call it a necessary cause, but it's clearly not a sufficient cause since most of the time, having sex does not result in pregnancy. Now let's talk about some errors in reasoning and how people have come up with causality in the past and why they may be wrong. So first, provincialism. This means we're understanding in our own terms based on past experiences and culture. But the problem with this is what makes sense to us may not make sense to anyone else, and we may have a misunderstanding of what's actually happening. Another is called the hasty conclusions. And this is where we settle on an answer to resolve an issue quickly. Now, it may make sense, but there may be other explanations that we didn't think of that might make better sense. We also may look at a logical cause that may become questionable later after some more evidence shows up. So other evidence may rise up to show that what we thought was a cause is actually unlikely. Now, once we have an initial conclusion about the important causes, we may ignore or suppress other information as irrelevant, and that could lead to actually missing some of the most important causes. And sometimes we fall under the spell of what we call the false dilemma, because we decide that there are actually two possibilities as a true cause, and we choose one over the other, which could be problematic because maybe they both are causes. There are two widely used sources that we use for criteria for determining causation. The first is a paper published by a British epidemiologist named Sir Bradford Hill, and the other is a report on smoking in 1964 from the U.S. Surgeon General. Let's talk about Bradford Hill. Now, Bradford Hill proposed a set of guidelines for assessing causality. He developed 9 to help us understand whether or not something was causal. And he did not really provide indisputable evidence for or against causation in this. So let's look at what he says causes causation. So here are the 9 things. We're only going to talk about 7 of them. So let's start with the strength of the association. So the argument is that the stronger the associations, the more indicative of the exposure being causal. He argues that if it is a extremely strong association, then you're less likely to have bias causing and muddling the results. So think about lung cancer and smoking. The critique, though, is that we should not dismiss small associations just because they're small associations. And we shouldn't always take large associations as being evidence of causality. Think about the ice cream and murder. The second is consistency of the data. Now, this is the idea that if I pull a sample out of this population today and I study the same question in a different population from a different part of the world tomorrow, and I continue doing that, pulling from different groups over different periods of time, if I continue to find the same association, so let's talk about smoking and lung cancer, if I find that in the 1970s among this group of people living in Georgia that smoking was associated with lung cancer, and in the 80s I pulled people from California, and in the 90s I pulled very rich people, and so on and so forth. If I continue to find that smoking led to lung cancer, the consistency of the data is enough of an argument that the relationship is causal. But there are also some good reasons for why these results might differ over time, so you can't dismiss things because the data is not consistent. Thinking about something like lead poisoning, okay? The people living in areas that have less amounts of exposure are not going to have the same levels of lead as people that have high amounts of exposure. So while poverty may be strongly correlated with lead poisoning, there may not be enough consistency of the data to show that, so you couldn't make a causal argument. Then there's specificity. Now, this says that a cause leads to a single disease or not multiple diseases, and that a given effect has a single cause and not multiple cause. And this really falls apart with most non-infectious exposures. It even falls apart with a lot of infectious exposures as well. Both of these assertions can be completely destroyed just thinking about smoking and lung cancer. Is smoking the only way that a person can develop lung cancer? Number 4 is temporality. This means that X has to happen before Y. So the exposure has to happen before the disease. And that any factors that coincident with the disease and factors that are a result of the disease cannot be causes of the disease. And there are no critiques of this. Pretty much every single person will agree that to prove causality, X has to happen first. Number 5 is the biological gradient. This says that different doses of exposure are associated with different associations in the outcome. And if that happens, then the exposure is likely to be a cause. So in other words, if the strength of the association increases as the exposure level increases, the association is more likely to be causal. So think about like radiation, right? That if you get just a little bit of radiation, you might get radiation sickness or cancer or even death, and that risk increases as you get more exposure to radiation. Now, the biggest critique of this is that it's a holdover from experimental laboratory studies, and it ignores the phenomenon that we call threshold effects, where that there are effects that everyone feels, and then it may drop off and it may come back. Number 6 and 7 are plausibility and coherence. So the assertion here is that biological and social models should exist to explain an association, and that an association should not be in conflict with current knowledge of natural history and the biology of disease. However, many epidemiological studies have identified cause-effect relationships before we even understood what the biological mechanisms were. So, for example, carcinogenic substances in cigarette smoke were discovered after the initial epidemiological studies linking smoking to lung cancer. The concept of causation in epidemiology is very different from the concept of causation in other types of scientific research. So, instead of seeking an underlying factor that leads to a disease, epidemiologists seek modifiable links in specific causal chains that will ultimately lead to the disease or other adverse health outcomes. This is part of a growing reflection of how epidemiology and public health are dedicated to the goal of prevention. So it's not necessary to understand every link in a chain of causal events. It's just necessary to interrupt a single link in the chain to disrupt the disease. The ultimate test for any epidemiological finding is the ability to show a difference in either clinical practice or in the general public health. This would often appear through primary, secondary, and tertiary preventions. The goal overall, though, is to push for primary prevention. So let's talk about these here in the next slide. Primary prevention seeks to interrupt a destructive chain of causal events. So, for example, if people are becoming sick from drinking contaminated water, we can make sure that they don't drink that water anymore. That is a modifiable link. We can stop the disease by eliminating the water source. Chains of causality leading up to this modifiable link may explain why a population has become exposed to unclean water. So maybe there's a war going on. Maybe there is sewage draining into a water line. We can look for those and we can stop it. We can also look at additional links on the causal chain to explain why the water is making people sick. So we can look for the types of diseases growing in the water. We can look for other types of toxins such as arsenic or lead contaminating the water. But the key point of this primary prevention is that we can find one of these links and stop it to keep people from getting sick. Secondary prevention involves the use of screenings for diseases, and this means that you already have the disease, and we're now trying to limit the impact that the disease will happen if it manifests. So, for instance, you have a high history of heart disease in your family, so you already have that coded into you somewhere. So now you're going to screen for heart disease. You're going to have your sugar levels tested, your cholesterol tested. You're going to get your doctor looking at your heart regularly, so cardiograms. You're going to be constantly monitoring your health to reduce the chances of suffering a heart attack. This means that we're going to narrowly focus on specific chains of causality. We're going to look at screening activities to test whether or not these screening activities are actually accurate and whether follow-up treatments are effective. This by making sure that people follow these screenings or follow-up treatments, or for instance, if you're prone to heart disease, maybe taking a low-grade aspirin a day. These are all links on the causal chain where we can break the risk that you are going to suffer. Finally, there's tertiary preventions. In this case, you've experienced the disease. So you've had that heart attack from the last slide. In these types of preventions, we're trying to reduce the negative impacts of established diseases. So in this case, we target the links in the chain that lead to better outcomes. So are there drugs that could help you like get back on your feet faster after your heart attack? Is there rehabilitative trainings that we can put you through? So occupational therapy, physical therapy that we can put your body through to get it back to being at the best health that it can be. You've had the heart attack. We can't stop that. You might have another one. We need to make sure that the time between is longer and that your body is better able to fight off the disease. We can also test the effectiveness of a drug or other treatment, and we can look at whether or not this will prevent the disease from reoccurring. When we think about causal chains, it's often better to think about them as like a spider's web. So we call them causal webs. And within this universe, our studies tend to be kind of opportunistic. So we're basically looking at the best opportunities to intervene in the processes of causation. Another way to view causation is through the component cause model. So think about the different causes as being pieces of a pie, and you need all the pieces for the disease to happen. So this proposes that there are these components that cause a causal relationship to happen through the combination of these things. This model creates a little bit of new terminology and kind of simplifies other terminology. So a necessary cause is present in each causal combination of the component causes. But then you may have a triggering or precipitating exposure that is one of the components of the causal mechanism. So for instance, let's think about tuberculosis. The necessary component cause is exposure to tuberculosis. You have to be exposed to the disease in order for the disease to become present. However, not every single person exposed to the disease is going to develop tuberculosis. So there are other factors that may be involved. Things like, have you been ill before? Have you had a pre-existing illness? Do you have a disease like asthma that may make you more prone to developing the disease? That's what we mean by triggering causes and necessary causes. Okay, let's stop here.